Now let's dive into more about how the RISC-V core and identify the machine code based on another example instruction, that is SUB assembly instruction. As you can see, this is the machine code. The corresponding instruction for this machine code is SUB assembly instruction. This machine code can be converted into binary format. Here, 0, 4, 0F, A, 0, A, 333, and this value can be converted into binary format. As you know, this binary value can be organized in the different format. That format can be identified in the bit assignment map. 0 to 6 bit, 7 to 11 bit, 12 to 14 bit, and each the binary value in different field has their particular meaning. So this binary value can be reorganized into the particular position. 0 to 6, as you can see, 0 to 6, 7 to 11, 7 to 11. Each value in the specific bit position has the different meaning. But as for 0 to 6 bit position, we can see the OP code. And 7 to 11 bit position, what you can see is the RD, that is the destination register. And as for the 12 to 14 bit position, you can see the functionality of this assembly instruction. This bit assignment map for an AND, SLL, SUB instruction can be identified in this RISC-V reference manual. If you're available, I strongly recommend you to open up this reference manual. Based on this bit assignment map, the first job of the RISC-V core does is to identify the type of the machine code, type of assembly instruction. For this operation, we need the three information. First one is OP code, second one is function 3, and the last one is function 7. Let's look at each the binary value in more detail. As for OP code is available 0 to 6 bit position. The binary value we have converted, we have 0, 1, 1, 0, 0, 1, 1. This is OP code. These binary value are available 0 to 6 bit position. But this binary value can be identified to this information 0, 1, 1, 0, 0, 1, 1. But in case of another assembly instruction like ADD, SLL, and as for this instruction, they have the same binary value in the OP code bit field 0, 1, 1, 0, 0, 1, 1 as for an instruction, and SLR instruction has the same OP code. Next thing we have to check is the function 3 bit field that is available inside 12 to 14 bit position. So please take a look at this. In this bit position, we can see the binary value is 0, 0, 0. Please take a look at this. Then 0, 0, 0 can be seen in this table. But as for the add assembly instruction, this instruction has the same value in the function 3. In order to check the more detailed operation of this machine code, we should refer to the bit field of the function 7, 24 bit to then 31th bit. As for this case, this binary value can be included in this table. The combination of the 3-bit value, the binary value, opcode function 3, the function 7, and we can tell that this machine code is SUB assembly instruction. This is the most important operation when the RISC-V core identify the machine code for the first time. Remember that the RISC-V core identified the machine code based on this binary format instead of hexadecimal format. Note that this binary value comes from this hexadecimal format. This hexadecimal value can be converted into this binary format. The binary value, binary format, they can be reorganized based on this bit position. Next important thing you have to do is to identify the destination register, the first source register, and the second source register. As for a destination register, we need to check the value in the 7th to 11th bit position. As you can see inside this, the bit flag, that is the 7th to 11th bit position, 1, 0, 0, 0, 0 value can be identified. If we convert this value into hexadecimal format, this value is 0x10. The value of 0x10 is identical to the X16 register. X16 register is architectural name of the register. This register can be called A6 register. Based on this information, we can have the A6 register used as destination register. If this value is 0x, 0x, F or D, and we can have the different destination register. Let's take a look at the first source register. As for this bit position, we can have this value and 0x10. For this reason, the first source register is A6 register, because in this bit position, we can have this binary value. But as for second source register, inside this bit position, we have 0xF. 0xF is identical to the X15 register. X15 register is corresponding to A5 register. For this reason, the second operand, the second source register is A5 register. Based on all of the information, including opcode, function 3, function 7, we identify that the machine code is SUB assembly instruction, and we got to know about destination register, first source register, that is A6 register, and we got to know about the second source register is A5 register. That is how the RISC-V core interpret the machine code in the binary format. So if you understand how the bit assignment map is organized, if you identify how the machine code can be parsed based on this bit assignment map, next thing and you have to do is to explore the form of RISC-V assembly instruction. This topic will be discussed in the next lecture.